Thank you. Thank you very much for the kind introduction, and thank you for the invitation. I'm just waiting for my slides to appear. Probably the next one. We'll see. There they are. Perfect. We already have heard something about non-target screening in the previous session by Katrine. Thank you for that. That saved me a lot of stuff to introduce now to you. And we also had a couple of presentations concerning metabolomics. So metabolomics is one of the disciplines that can be summarized as non-targeted analysis or non-target screening. And the speciality for us is we're not a research facility, we're a private company. So we have a lot of different services that we provide. We can do a lot of consulting and education. So when a laboratory wants to do non-target screening, we can help them to do that. But on the very right side, you can see what is related to this topic today. We're also a contract and test laboratory. So we do a lot of sample analysis in a non-targeted way. So we have run about 1,000 samples this year already. So customers come to us with a specific question, and we use our methodology to answer this question. So we are out of these disciplines that you probably know, metabolomics, lipidomics, and so on. We work in all these fields, but we are not restricted to one of these fields. And we already had a definition of non-targeted analysis by Katrine. We have a bit of a different definition. It's a bit broader. So what is non-targeted screening? In our perspective, it is a comprehensive and untargeted analysis. This means we want to catch as much compounds that are contained in a sample, analyze and detect those, and then do data evaluation, so getting the most interesting compounds in the sample, and then do a statistical data interpretation. And that's exactly what I want to show you today, what we can do with our technology with coffee. How do we do that? We mostly rely on liquid chromatography coupled to high-resolution mass spectrometry. We already heard about that in the last session. And then what you can see here on the very right, that's what our raw data is like. In the coffee samples, we had approximately 20,000 different signals that we had detected. Obviously, not all of these are relevant. So we need to combine the metadata that we have from the samples with our raw data and find out which are the really relevant compounds or signals in your sample, in our sample. Therefore, we use blank subtraction, filtering, and a selection. And at the end, we might end up with some hundreds, some thousands of compounds, which we then can use, do statistics with, and set in correlation with the metadata that we have. So much for the introduction. What have we done with coffee? Thankfully to Dr. Schwarz, we had a quite nice set of samples prepared by Katarina. Thank you for that. That consisted of two different conditions of coffee. So we had green and roasted coffee. In these green and roasted coffee, there were two varieties. This was Arabica and Canephora. We had different ripeness stages, like ripe and semi-ripe, different processing stages, natural, semi-washed, and washed, and different fermentation times. All in all, this added up to 96 samples. Since we do a lot of statistics, we need replicate measurements, and so we did triplicate measurements, and they all added up to nearly 300 different measurements that we had to conduct. So how did it look like? Let's have a look into the green coffee. On the left side, there you can see the raw data of the green coffee. We have a special type of chromatography that allows us a bit to categorize compounds, and the samples were extracted in 80% methanol, so more likely organic extraction, but we were surprised that we had a lot of polar and very polar compounds in there. So that's exactly what you would expect if you have an aqueous extract, and what you expect in a cup of coffee to find. So after all this filtering, we ended up with the plot there on the right side, and then we talk about 1,500 features starting from these 1,100. So there you can see how important it is already to do this blank subtraction and the filtering, because that significantly reduces data. And yeah, that plot is not showing you anything. You just know that there is a lot of compounds in there. So I just want to take you on a journey with me into the cup of coffee. that's the principal component analysis of the data set. We just tried to have a perspective from the top to the bottom, and so we just started looking into the different coffee species. And we can there already see that we can easily differentiate Canifera and Arabica. The question is now, we also had different data sets. There is one Canifera, for example, that is sticking out over there. At that stage, I cannot say why. It's just a statistical anomaly that this seems to be a bit different. But as you can see, the triplicate measurements, they fall together. So that's not an exception, but that sample seems to be different at all. We also had different ripeness stages. And as you can see here, we have on the left side, blue is ripe and yellow is semi-ripe. We cannot see there any trends in there in Arabica and Canifera because the data set is quite complex and quite large. But I can show you later, the deeper we go into these data sets, the more differences we can see. But PCA probably is here not the right one to differentiate these samples. The same is true for the processing. Of course, we can see that there are natural semi-washed and washed samples, but within the Canifera or the Arabica, it is really difficult to say what is the effect of the different processing. If we look into roasted coffee, also the PCA here, you can see still we can differentiate Arabica and Canifera, but they seem to be a bit more together. So there is still a difference, but probably not in the same amount as before. And also here, there's something sticking out. It's not a Canifera, here it is an Arabica. That seems to be different. Maybe something happened there in the processing or in the roasting that just made it to look different. Also looking here into the ripeness and the processing, same picture as before. PCA seems not to be the one that can be used to get an information about what processing stage might be making a difference in the coffee or which ripeness state. Here in this plot, we have put all of the coffee samples together. So before we had green coffee and roasted coffee, and here we put them all together. And that's quite nice because we saw already that we can easily differentiate Arabica and Canifera, and here we can see we also can differentiate the green and the roasted coffee. A little fun fact, maybe you can see on top in the Canifera roasted, there are two light green points in there. There I've just added my home brand coffee because I wanted to know how my home brand coffee looks like in the whole data set, because that's always a problem if you have a rather homogeneous set of coffees, and that's the case here because this was all the same type of coffee. It is difficult to see how high the variation really is, because a PCA will probably always show you differences, but you might be in the case that you interpret them as really large differences, although you have just a small picture of a sample. But in that case, the coffee also falls in there, so it is not so homogeneous as probably expected. Yeah, here at PCA, we already saw we can differentiate now between the different species and the different stages. Now looking a bit deeper, because here we just talk about the samples, but in the background there, we have 4,500 different chemical compounds which we have detected. And what we can do here is a volcano plot. In this volcano plot, we can compare green versus roasted. On the very left side, you can see those compounds which have a higher signal in green coffee compared to roasted coffee. And on the right side, you can see the compounds which have a significantly higher signal in roasted coffee